will be focusing on ship stability and stresses of ship experience in the water. We cover metacentric height and its role in stability, the concept of initial stability, and finally, show how we can determine the type of stress acting in ship hull supply by analyzing its forward, after, and midship draft. A diagram illustrating the center of buoyancy or the V center of gravity and the metacenter of a ship and small angle of heel. Include labels for the waterline, heeled waterline, and vertical distance of GM. In the bullet points, the vertical distance between the center of gravity or G and the metacentric of or M of a vessel is a crucial indicator of a ship. Initial static stability against small angles of heel determine the magnitude and rotating moment that restore the ship to an upright position. To larger positive GM generally indicates greater initial stability. Let's start with metacentric height, often abbreviated as GM. Imagine a ship floating upright is weight downwards through the center of gravity or G, and the buoyancy of force act upward through the center of buoyancy. Now, if the ship heels slightly, the shape of submerged buoyant change, causing the center of buoyancy to shift to a new position. If we draw the vertical line upward from this new center of buoyancy, it intersects the ship center line at a point called metacenter or M. The metacentric height is the vertical distance between the original center of gravity and this point of metacenter. GM is a vital measure of ship initial stability. A larger positive GM means that for a small angle of heel, the rotating moment, the force that tries to bring the ship back upright, is greater, indicating better initial resistance to capsizing. The uses of metacentric height in stability measurement. Predicting initial stability, a primary indicator of how the ship will respond to small disturbance, wind, waves, turning, assessing resistance to rolling, influence the ship's natural rolling period. A large GM often results in a shorter, potentially less comfortable roll period stability criteria. So the compliance is regulatory bodies set minimum GM requirements for different types of vessel and loading conditions to ensure safety. Loading and ballasting guidance is used to calculate the GM for various loading conditions and guide ballast operations to maintain adequate stability. So, how do we use this metacentric height in practical terms? Firstly, it's a key predictor of ship's initial stability. A sufficient GM ensures the ship will be readily returned to an upright position after being slightly inclined. So secondly, GM affects the ship rolling motion, while a large GM provides good initial stability. It can also lead to quick and jerky rolls, which might be uncomfortable for a crew and passengers and could potentially put stress in the cargo and hull. Conversely, a very small GM can result as sluggish roll but may compromise the stability. Importantly, international regulations establish minimum GM values the ship must meet under various operating conditions. Naval architecture uses GM calculation extensively when planning cargo loading and ballast operation to ensure the vessel remains within safe stability limits. Now, let's talk about the initial static stability. This refers to a ship's inherent ability to resist small inclination and return to its upright position once its turbine force is removed. It's essentially the springiness of the ship in the water. We quantitate this stability using the rotating moment or RM is the turning effect of pushes the ship back upright. So the rotating moment is calculated by multiplying the ship weight, which is equal to its displacement, by the rotating lever or the GZ. The rotating lever is the perpendicular distance between the line of action of the buoyant force in the line of action of the weight. Initial static stability. A diagram showing a forces acting on a heeled ship weight or acting downwards through the gravity and the buoyancy acting upward illustrate the righting lever. So the tendency of a ship to return to its upright equilibrium position after the being subjected to all small external stirring, force or wind or gust, small or wave, quantified by righting moment P or Rm, which is the product of the ship displacement in the weight and the righting lever for a small angle of heel. The righting lever is approximately equal to Gm sine, so therefore the Rm is equal to weight times Gm sine. Then this show the direct relationship between Gm and initial static stability. For small angle heel, there is a useful approximation. The righting lever Gg is approximately equal to metacentric height multiplied by a sine of the angle of heel or sine then give us the formula for the righting moment. Rm is equal to weight Gm times sine. This equation clearly shows the larger metacentric height leads to a larger righting moment and thus greater initial static stability. So, we're determining the stress type from the graph readings. So, the simple sketches of a ship are showing hugging mid-ship a drop is a less than the average of the forward and the after drop. The ship looks like in arching upward in the middle. Sagging mid-ship drop is a greater than the average of the forward and after drop. So, the ship looks like it's bending downwards in the middle. So, the even keel is a forward, after, and midship drop are approximately equal. So let's analyze the forward and after and midship drop. We can infer the primary type of longitudinal stress ship hull is experiencing hugging occurs when the midship drop is less than the average of the forward and the after drop. So the other side is dispute the deck under the tension and the keel under compression. So the sagging occurs when the midship drop is greater than the average of the forward and the after drop. So the other side is dispute the deck under compression and the keel under tension. Even keel occurs when the drop forward, after and the midship drop are approximately equal. Ideally, there is a minimal longitudinal stress in this condition. So let's shift our focus to how we can understand the stresses acting on the ship by looking at its draft readings. The draft are the depth of the ship below the waterline of different points, forward, after, and amidship. By comparing these readings, we can determine if the ship is experiencing hugging and sagging. Hugging occurs when the midship drop is less than average of the forward and the after drop. Imagine the ship bending upwards in the middle like hugging back. In this condition, the deck experiences tensile stress is being stretched, while the keel experiencing compressive stress and it's being squeezed. Conversely, sagging when happens when the midship drop is greater than the average of the forward and the after drop. Pictures of the ship bending downwards in the middle, like a sagging beam, as the deck is under compression and the keel is under tension. When the forward, after, and the midship drop is nearly equal, the ship is said to be an even keel, and ideally it experiences a minimal longitudinal bending stress. So, let's analyze answering the specific question in final written to 37 to 40. So, first is you need to answer the 37, 38. So, by analyzing a specific condition draft. So, first is the scenario is forward is 10 meters and after is 11 meters. So, the midship is 10.80 meters. By calculation, the average of forward and after drop is equal to 10 plus 11 divided by 2 is equal to 10.5 meters. So the comparison is the midship drop is 10.80 meters is less than average drop of 10.5 meters. So my conclusion is sagging condition. And by addressing this question, the 738, let's now apply what we learned to your specific question for question 3738. So that the given draft are forward 10 meters and the after is 11 meters. and the midship is 10.80 meters. First, we calculate the average of forward and the after drop. 10 plus 11 is divided by 2, which is equal to 10.5 meters. Now, we compare the midship drop is 10.80 meters with this average 10.5 meters. So, since the midship drop is greater than the average drop, the ship is experiencing a sagging condition. Therefore, for question number 37, is the keel of the midship will be experiencing the tensile stress during sagging. And for question number 38, is deck of the ship will be experiencing compressive stress during sagging. So this time, we compare the midship draft 10.40 meters within the average 10.5 meters. Since the midship drop is less than the average drop, the ship is experiencing a hugging condition. Consequently, for a question 40, the keel of the ship will be experiencing compressive stress during hugging. And for question number 39, the deck of the ship will be experiencing tensile stress during hugging. In conclusion, the metacentric height Jm is a key indicator of initial static stability. Initial static stability is the ship's ability to return to its upright position after small disturbance, analyzing forward, after, and midship draft. It helps determine if the ship is experiencing hugging, deck tension, keel compression, and sagging. The deck compression, keel tension. In summary, we discussed how metacentric height provides a crucial measure of a ship's initial stability, and how initial static stability in the fundamental tendency of vessel to remain upright. We also seen how a simple comparison of forward, after, and midship draft can give us valuable insight into a longitudinal stress, hugging, sagging, acting the hull ship. That's all, and thank you. Have a good day.
Thank you for watching.